Hello everybody. So in this particular video lecture we will look into the marine evaporites. So whenever we listen the term evaporites, immediately three different things comes into our mind. First one is gypsum, formula is CaSO4 2H2O. Second one is anhydrite, formula is CaSO4. Third one is normal table salt, or scientifically that is called here halite. Most of the composition of most of the halite is here NaCl. So these three are the major and most common evaporites that occurs normally naturally in our environment. Now these three evaporites, as we all know, these three evaporites normally deposits or precipitate from the ocean water. They normally precipitate from sea water when the same sea water undergoes evaporation. That means these three different evaporites normally formed by means of the evaporation of the seawater, and at the same time whenever evaporation normally takes place, when the evaporation of seawater normally takes place, the volume of the seawater normally reduce. The volume of the seawater normally reduce. Now a point that is relatively important to remember, ki the gypsum normally form when by means of the evaporation the seawater reduced to 19% of its volume. Gypsum normally formed when the seawater by means of the evaporation reduced to 19% of its volume. Similarly, the halite normally precipitate from the seawater when the volume of the seawater reduced to 9.5% of its original volume. So the gypsum normally precipitate when the seawater reduced to 19% of its volume. Similarly, the halite normally deposits or precipitate when the seawater reduced to 9.5% of its volume. So although we have seen the evaporites normally formed by means of the evaporation process, by means of the evaporation of the seawater, but this process is not so simple. Instead, or in a more elaborative way, the evaporites normally form when a body of water is partially isolated. A body of water is partially isolated from open ocean. From the open ocean. This is the first condition that is required for the precipitation of evaporite deposits. And second one, only this isolation will not work. In fact, only this isolation will not work. Instead, this body of water, it must be present in arid climatic setting, or it must be present in arid climate. That means when a body of water is partially isolated from the open ocean in an arid climatic setting, the evaporite start to deposit. So first we will see why we need a partially isolation of a body of water from the open ocean. Why not, or what would happen if a body of water will be completely isolated? See, these evaporites are nothing but they are simply the precipitation of dissolved component. They are the precipitation of dissolved component that are actually present in the seawater. Therefore, if the water body will be partially isolated, that means the seawater is replenishing at a constant interval or in the regular interval. Okay, but if the water body will be completely isolated from the open ocean, that means there will be no exchange of water between the open ocean and that particular shallow body of water. That means there will be deposition of evaporites, but the thickness of the evaporite layers will be relatively less. Therefore, if the water body will be partially isolated from the sea water, then what will happen? There will be exchange of water between the open ocean and that of the shallow body of water, so that more and more amount of sea water will enter into that shallow body of water, that will again evaporate, and a very thick layer of deposits or thick layer of evaporite deposits normally results. There will be a deposition of thick layer of evaporite deposits. Second, why we need a arid climate? See, for the evaporation we need a dry and warm climate. We need a dry and a warm climate, and we all know that this dry and warm climate is normally present in the arid climatic setting. In the arid climatic setting. Therefore, the evaporites normally deposit when a shallow body of water is partially isolated from the open ocean in an arid climatic setting. In a arid climatic setting. If we look into the chemical process, or if we look into this process in a chemical way, then the evaporites normally form when, by means of the constant evaporation, the sea water reaches its supersaturation, or the salinity of the sea water reaches its supersaturation, and we all know if the salinity will increase more than the supersaturation point, immediately the precipitation of the mineral will start. The precipitation of the mineral will start. Therefore, the evaporites normally deposit when, by means of the evaporation process, the salinity of the sea water reaches its supersaturation point, and if the salinity will increase more by means of the same evaporation, then immediately there will be precipitation of the evaporites, and the shallow water region where the evaporites starts to form or starts to precipitate, they are called saline giants or bared basin. They are called your saline giants or your bared basin, and most of the bared basin or saline giants, they are the very small ocean. They are very small ocean, they, which are normally separated from a large ocean by means of a strait. By means of a strait. This strait is a shallow connection. It is a shallow connection between an open ocean and a partially isolated body of water. Okay, and by means of the tectonic uplift or fall in the crust, fall in the oceanic crust, if this small ocean will be partially isolated from that open ocean, then immediately a precipitation of the evaporites will take place. Precipitation of evaporites will takes place. Previously we have seen that for the evaporites to form, there must be limited exchange of water. There must be limited exchange of water between that partially isolated body of water and that of the open ocean. This is required because as we have seen if there will be a slight exchange of the water, then more and more amount of water will be evaporated and a thick layer of evaporites will result, or thick layer of evaporites will deposit. In essence, for deposition of 1 meter of evaporites, for the deposition of 1 meter thickness of the or for the deposition of evaporites of thickness 1 meter, it needs evaporation of 75 meter of the seawater. That means when a 75 meter thick of the seawater will evaporate, only 1 meter of evaporite will result. 1 meter of evaporite will result. So I hope you can imagine for the production or for the deposition of approximately 100 meter of evaporite deposits, how much amount or a very huge volume of ocean water or huge volume of sea water needs to be evaporated. Now if we look into the evaporite basin, then the evaporites can deposit in 3 different type of basin condition. First one is shallow water deep basin setting. Shallow water deep basin setting. Now in this particular condition, the basin is deep but it contains relatively very less amount of water, therefore the water is always shallow in nature, or the depth of water is not much more high. It contains a shallow volume of, or very low volume of, evaporating seawater. It contains shallow or low volume of evaporating seawater, but by means of the periodic overflow from the open ocean to this basin, after some time a very thick volume or a very thick layer of evaporites normally results. Now the evidence of this deep basin setting normally comes from the presence of turbidite deposits, because we all know that these turbidite deposits or this turbidity activity or turbidite activity is only found in the deep basin setting. Therefore the presence of turbidite deposits within these evaporite deposits is an evidence that indicates that these evaporites are normally deposited in a shallow water to deep basin setting, in a deep basin setting. Also this point is important. For the deposition of evaporites in a shallow water to deep basin setting, the evaporating seawater must be replenished at a regular interval. Otherwise, what will happen? There will be the deposition of evaporites, but only a very few meter thick or very less thickness of the evaporites will deposit. Second one is shallow water and your shallow basin setting. In shallow water, shallow basin setting, although the basin contains a very shallow amount of water or very low volume of water, so you may assume how this particular setting will produce a relatively thick layer of the evaporite. Now in this particular setting, a very thick volume of evaporites will only result if this basin will continuously subside. Again I am telling in this shallow water, shallow basin setting, a very thick volume of evaporites will only result if the basin subside frequently or in a continuous manner. So that although the basin contains very low volume of water, but due to the continuous subsidence of the basin, gradually a very thick layer of evaporites will result. Third and most important evaporites basin is your deep water deep basin condition. Deep water deep basin condition. Now this deep water deep basin conditions or deep water deep basin of the evaporite deposition, this deep water deep basin conditions of the evaporite deposition, they are normally completely isolated from the open ocean, but previous two are only partially isolated. But in this case, in this deep water deep basin setting, the evaporite basin is completely isolated from the open ocean. This evaporite basin, or the region where evaporites are continuously deposited, it is completely isolated from the open ocean. And another very important thing is that in this particular setting only, the evaporites normally deposits at the margin of the basin, but in previous two basin, the evaporites deposit at the center of the basin, Now when the evaporites will deposit at the margin of the basin, and later on by means of the gravity flow, all these evaporites will transfer into the center of the basin. All these evaporites will transfer into the center of the basin. So these are the three different types of basins where we can expect the formation or deposition or precipitation of the evaporites. I think you all know this particular term, lagoon. Okay, and geologically the lagoon can be defined as it is also a shallow body of water that separates or that is situated between the main continent and the your open ocean. So you may think ki sir, whether the formation of evaporites is possible in this particular lagoonal setting, then the answer is no, because the major difference between the lagoon and the saline giants or the evaporites basin is that ki saline giants are capable of accumulating or depositing a thick volume of evaporites, but in comparison to the saline giants, these lagoon are much more shallow. They are much more shallow, and due to their due to their very low depth, this lagoon cannot accumulate relatively high or relatively thick volume of evaporites. Now this deep basin setting, this evaporites of the deep basin setting is again of two types. If the deep basin is completely isolated from the open ocean, you can see here, if the deep evaporite basin is completely isolated from the open ocean, then with the increasing magnitude of evaporation at the margin, we have the very less soluble compound, that is your calcium carbonate. That means in this deep basin, under the condition that the deep basin is completely isolated from the open ocean, at the margin of that particular basin, we have calcium carbonate deposit. Calcium carbonate at the margin. Okay, and as the gradually magnitude of evaporation will increase, there will be deposition of gypsum, and finally at the center of the basin we have the halite deposits. We have the halite deposit. That means in this particular or in this typical type of deep basin or deep evaporite basin, we have the deposition of calcium carbonate at the margin and halite at center. Halite at center. That means from margin to the center, from margin to the center, the salinity increases. The salinity increases, and this typical type of evaporite deposits is called your bull's eye pattern. It is called your bull's eye pattern. That means in your bull's eye pattern of evaporite deposits, we have deposition of calcium carbonate at margin and deposition of halite at the center, and from periphery or from margin to the center, we have an increase in the salinity gradient, or we have a increasing salinity gradient, and this is called your bull's eye pattern. But if the deep basin is only partially connected, or it has a very limited connection with the open ocean, then near this connection point the water is always of low salinity. Water is always of low salinity. Therefore, whenever there will be deposition of the material, immediately calcium carbonate will deposit. The calcium carbonate will deposit. But in this particular margin, which is far from this connection point, we have a very high salinity value due to your due to the high evaporation, due to the very high magnitude of evaporation, and there will be deposition of there will be deposition of halite. That means in this particular basin, where a deep basin or deep evaporite basin is partially connected with the open ocean, near the entrance or near the point of connection, we have a low salinity water. So if there will be deposition, then the calcium carbonate will preferentially deposit. But at the margin, which is far from this connection point, between this evaporite basin and the open ocean, we have relatively high salinity value. Therefore, if there will be deposition, then halite will deposit. That means if we look into this particular basin in terms of salinity gradient, then near the point of connection to the center, there will be no salinity change. Instead, here it will show the isohaline condition. same salinity condition, but on the exactly opposite side of this connection point, or exactly opposite side on the exactly opposite side of this point of this connection between this basin and the your open ocean, from periphery to the center, we have the decreasing salinity. Therefore, and this particular type of evaporite deposits give rise to a pattern that is called your teardrop pattern. That means in your teardrop pattern of the evaporite deposits, we have the deposition of halite at margin and deposition of calcium carbonate at center. Deposition of halite at margin and deposition of calcium carbonate at center, and from periphery or from margin to the center, the salinity value decreases, which is exactly opposite to the bull's eye pattern. Apart from this, the type of evaporites that will deposit in a evaporite basin is also dependent on the seawater chemistry and the volume of seawater. For example, if there will be rise in mean sea level, rise in mean sea level means there occurs the addition of fresh water to the ocean, okay, and whenever fresh water will be added to the open ocean water, immediately the salinity of the open ocean or salinity of the open ocean water, it will decrease, and under this decreasing salinity condition, calcium carbonate will start to deposit. Similarly, if there will be fall in mean sea level means definitely some amount of water from the open ocean has been removed. It has been removed from the system, and as the ocean experience the loss of fresh water or loss of water, therefore the salinity value will increase, and under this high salinity condition, halite will deposit. That means an alternation between the rise in mean sea level and fall in mean sea level is also reflected in terms of alternation between the calcium carbonate deposits and the halite deposits. And one of the most famous location where we can find a very thick accumulation or very thick layer of evaporites is your bottom of the Mediterranean Ocean. In the bottom of the Mediterranean Ocean, and that particular dry event that has causes the entire water of the Mediterranean Ocean to evaporate is called your Messinian salinity crisis. This is your Messinian salinity crisis. So this is all about the how evaporites normally formed and what are the different patterns in which the evaporites can deposit. Thank you. Bye bye.